In this video, we're going to talk some more about congruent triangles. Okay, and when we say this notation, triangle ABC is congruent to triangle DEF, we're actually saying more than just the two triangles are congruent. We're saying that all six corresponding parts are congruent. So specifically, side BC is congruent to side EF, AC is congruent to D, F, and AB, the first two here, congruent, D, E, those there. So the angles, the interior angles at A is congruent to the one at D, the one at B is congruent to the one at E, and the one at C is congruent to the one at F. So here's an example of this illustrated with congruent triangles in Euclidean geometry. These are constructed in such a way that as I manipulate these three yellow points, then this figure down here, notice it always stays congruent to the one up here. So triangle ABC is congruent to triangle DEF. So sometimes we'll use a mark like this. A single mark right here will indicate that those two sides are congruent. Double mark that these two are congruent. Triple mark here. Sometimes we'll do it by color. And notice here I've color coordinated the sides. And of course, if those of the links are equal, then those sides are congruent. And so the green here corresponds to the green sides here and their links. Similarly for the blue. Notice that the blue, I use the blue angle marker opposite the blue side. So just some other terminology with triangles. We say that the angle A here, that is the angle BAC, that interior angle at A, is opposite side BC. Okay, so that is basically what we mean by an opposite side. And then we say that this angle is included in these two sides, or these two sides form that angle. They don't really, remember the angle actually is not really the two sides, it's the rays AC and AB together form that angle. But we say that these two sides include angle A. And then the other side is the side that's opposite angle A. So there's some terminology there as well. Okay, so what are the major things that we want to investigate? And really the main focus of this week's tasks are all to investigate in the various geometries, Euclidean, taxicab, hyperbolic, and spherical geometries, if we can get by with less than this. You know, here we have 6 pieces of information. Could we get by with just maybe 5 of those and make the 6th one for free? Or maybe 4, or maybe 2, or whatever. Of those 6 correspondences to be corresponding parts that are congruent, is that enough? And specifically, we're going to mainly investigate this week in which cases is 3 pieces of information enough. In other words, if I'm given, for example, that this the BC is congruent to EF, and side line segment AC is congruent to line segment DF, and line segment AB is congruent to DE, is that enough to conclude that we get these corresponding angles congruent down here? Or vice versa, if we get the 3 corresponding angles congruent, is that enough to conclude that the corresponding sides are congruent? Or some combination of sides and angles where we have 3 pieces of information. Is that enough? Well, if you look at it a little bit, there are actually 6 ways we can do this. We can have 2 sides in the included angle, that's side, angle, side. The 3 sides, side, side, side. 2 angles in the included side, angle, side, angle. 2 angles in a side where that side is opposite that angle, so angle, angle, side. The 3 angles. Or 2 sides in an angle where that angle is opposite that side there. Now when we're investigating these, we're going to investigate with 2 perspectives. Okay, 2 different conditions. So one way we can look at side, angle, side, for example, is we're given 2 different triangles, so we know the 2 triangles exist, and we know that they have 2 pairs of corresponding sides that are congruent, and the corresponding pair of angles included in those 2 sides are also congruent. Then the question is, do we or do we not have enough information at that point to conclude that the 2 triangles are congruent? And the answer may or may not be different in the different geometries. That's really your main task for this week, is to try to figure this out. Okay? Another way we can look at this perspective is if I give you three measurements. Okay, so notice the way I just said it before when I had the two triangles, I didn't tell you what the measurements were. I just said that they correspond. So here I'm not necessarily telling you, for example, what the measurements of these are, but for example, maybe I tell you that the green sides are the same, are congruent, the blue sides are congruent, and the red sides are congruent, not what they might be. In fact, we can maybe think of them as being variable. Is that enough to make the angles congruent? Yes or no? That's a question that we want to investigate. Now, another way to look at this is basically think of just one triangle, but I specify, some angle for angle A. Then I specify a length for the side AC and a length for side AB. Is that enough to determine exactly what's going to happen with the lengths of the other side, the length of the other side, and the measure of the other angle? So there's two ways to look at the side angle side condition right there. And the same thing is true for each of these. So just some terminology here. When we're comparing two triangles, we can talk about the two triangles or a triangle to itself are in correspondence with each other if and only if we're referring to a bijective correspondence, bijective mapping, between the two triangles such that the vertices correspond to vertices and sides correspond to sides. So that's any kind of correspondence. And the side angle side condition says, we say a pair of triangles, or a triangle itself, have the side angle side condition, SAS condition, if and only if the two triangles are in correspondence so that the two pairs of corresponding sides are congruent and the pair of corresponding angles included by these sides are also congruent. SSS, we say that a pair of triangles or triangle in itself have the side-side-side condition, SSS condition, if and only if the two triangles are in correspondence so that all three pairs of corresponding sides are congruent. The ASA condition is if two triangles are in correspondence so that two pairs of corresponding angles are congruent and the pair of corresponding sides included by these angles are also congruent. We say that a pair of triangles or triangle itself have the AAS, angle-angle side condition, if and only if the two triangles are in correspondence so that two pairs of corresponding angles are congruent and the pair of corresponding sides opposite one of the pair of corresponding angles are congruent. So think of like that first angle as opposite that side. Side-side angle, we say that that condition is met if the two triangles are in correspondence so that two pairs of corresponding sides are congruent and a pair of corresponding angles are opposite one of the pair of corresponding congruent sides are congruent. So in the side-side angle condition, think of that first side as being opposite that angle. And then, of course, the AAA condition, their angle-angle-angle condition, is if the two triangles are in correspondence so that all three pairs of corresponding angles are congruent. So notice that these definitions require that one part of a triangle be congruent to a corresponding part of another triangle, actually three pairs of those, but they do not require that parts of the same triangle be congruent to itself. So when I say side-side-side condition, I'm not talking about an equilateral triangle necessarily where the sides are congruent to each other within a triangle. I'm talking about the side from one triangle be congruent to the side in the other triangle. So again, looking at our picture, it's that the green side is congruent to the green side, not that maybe the green and blue are congruent. Now, if we look at definitions and notation with one triangle, we use the notation length 1, angle measure length 2 to indicate the measure of two sides of the triangle, the measure of included angle. So for example, we might say a 2 centimeter, 1.3 radian, 5.6 centimeter triangle. This means that the triangle has sides of length 2 centimeter and 5.6 centimeter, and where those two sides meet, the angle formed has a measure of 1.3 radians. The side-side-side condition, we're given length 1, length 1, length 2, and it says these are the three sides of the triangle, the measures of the three sides. So, for example, we might have a 2 centimeter, 4 centimeter, 5 centimeter triangle. Okay, and we have the, so for in the AAS condition, we might have angle measure 1, angle measure 2, and then length. So this would be 2 interior angle measurements, and then the measure of the side, and the side that you list last has to be opposite the first angle. So for example, if we say a 2 radian, 0.3 radian, 5 centimeter triangle, the 5 centimeter measurement of the side is opposite the angle with a measure of 2 radians, and of course it will be next to one that has 0.3 radians. Side-side angles, we use length 1, length 2 angle measure to indicate the measures of the sides and angles, but this time the angle is opposite that side with length 1. For example, we have a 5 centimeter, 2 centimeter, 1.3 radian triangle. What that means is that those are the measures of 2 sides and the angle, but more than that, that the 1.3 radian measurement angle is opposite the 5.6 centimeter side. And of course, angle, angle, angle just means those are the 3 angles. For example, we could have a pi over 3 radian, pi over 6 radian, pi over 2 radian triangle, for example. So notice that these measures basically go around the figure in either a clockwise or counterclockwise order. So I might, for example, be given, so like in the side angle side, well, let's say angle, angle, side. I might be given this angle measurement, and then this side, angle, angle, side. So angle A, angle B, and then side, the blue side here is BC. Okay, where that's opposite angle A. Or it might go the other way. That was going kind of counterclockwise or clockwise. Now, what if we want to go counterclockwise? Well, we might know this angle, then this angle, and then this side. So we might know angle C, then angle B, and then the side up here. So you can read these around either way. Of course, if you read this one backwards, angle, angle, side becomes side, angle, angle, which is really the same thing, but we prefer the notation angle, angle, side. And for example, SSA, of course, would be also ASS if you did it backwards, and for maybe obvious reasons we prefer SSA. So, basically, your tasks this whole week are dealing with this idea of triangle congruence and trying to decide under which conditions these work. Now, the first task, we'll come back to the first task, which you actually will probably do last. So, task 1 is basically constructing triangles and measuring the interior angles and then looking at the sum of those interior angles. And doing that in general for Euclidean, taxicab, hyperbolic, and spherical geometry. Okay? And spherical just says do 4 different ones. In Euclidean geometry, you can just make a dynamic one and move it around, and you're doing thousands of examples. Tasks 3, 4, 5, 6, 7, and 8, all of those tasks are dealing with different situations there of sets of congruences. And so, for example, task 3 is about the side angle side property. So what we want to do here, I'm giving you some, so we're sort of taking the second perspective, is where I'm giving you some specific measurements, and you have to build a triangle with sides of length 4 centimeters, 6 centimeter, and the included angle being 0.45, of course that's radians. Okay? Measure the interior angles and lengths of each side of that triangle. Is it possible to make another triangle with those same measurements, but different other measurements? In other words, the 4 centimeters, 6 centimeters, and 0.45 radians, where the 0.45 radians is between the 4 and 6, is it possible to make a different one? If not, sort of convince yourself that that's not possible, and kind of maybe informally why that's true. And if it is possible, then make another one. And then answer the question, is it enough? And then basically do the same thing for the others. The measurements have been adjusted, hopefully, to make things fit a reasonable size on the page. And those you're going to have to use some of your tools taxicab tools, hyperbolic geometry tools, and Euclidean tools in Sketchpad. Task 4, similar thing. Given three sides here, come up with the measures of the angles. And again, is there more than one way to do this or not? Same way for ASA property, AAS property, SSA property, and AAA property. Okay? Then we come back to task 1, and task 1 kind of is, after you've done the others, is kind of a summary. What can you say about the angle sum in each of these 4 geometries? How many congruence classes of triangles are possible? We didn't prove that congruence of triangles is a equivalence relation, but in fact it is. And so these form equivalence classes. All the triangles congruent to itself. Any triangle that it's also congruent to is also in the same congruent class. So it's pretty clear that we get an equivalence relation there. So we have congruence classes. Okay, and so with these particular measurements of 3 centimeters, 4 centimeters, and 10 centimeters, how many congruence classes are available or possible that fit in there? Maybe it's 0, maybe it's 1, maybe it's 2, maybe it's 3, 4, 5, infinitely many. You have to decide how many different classes there could be there. So we're talking about counting the congruence classes. Okay? And this is in Euclidean geometry specifically. So you can do this, you can investigate these in Sketchpad, you can investigate them on pencil and paper. All I really need here is, I mainly just want a number for an answer. Although if you want to include some explorations on the right or something, you can make some hide show buttons for that too. But I'm basically going to grade this just with a number for it. Question number 3 says, okay, if I've given arbitrary choices, not these specific ones, but just arbitrary choices for these, what are the possibilities for how many triangles are possible? Again, I'm counting equivalence classes. So perhaps in a certain situation, there are certain numbers that would make only 1, and certain other numbers that would make 2, and certain other numbers make 0. Or certain numbers, maybe no matter what you get, you can always get infinitely many, or maybe it's 0 or infinity, or just give me the different possibilities where you don't really know what the numbers are. And if it includes a case where there's no possibility that you could make up some numbers in such a way that there are no equivalence classes of triangles possible, no triangle even exists, what kind of conditions then would guarantee that that there would exist something? So there are a couple of these that if you have certain conditions, then it won't, no triangle is possible. I'll say there's at least one that does that. Okay, and so those 2 questions, 2 and 3, are strictly about Euclidean geometry. And number 4 now is taking the other perspective where I talk about we have 2 triangles in the indicated geometry. And the question is there enough, if you're given these conditions, is there enough to guarantee the congruence of the triangles? And just type in a yes or no in the cells. Of course, this is not a real table like you have in Word, but you can click on here and go across here, and type no or yes, whichever is appropriate. Okay, and so really task 1 is mainly just a summary of what you've kind of seen before, and in the case of number 2, it's sort of more examples of what you've seen in the other, what you did in the other tasks, but specifically with Euclidean geometry. Our task that we're going to do on Friday is going to be a lot like some of this stuff, particularly task 2, that we're going to do that in Euclidean geometry.